Hello. Today we will be solving this problem called digit queries. So consider an infinite string that consists of all positive integers in increasing order, 1, 2, 3, and so on. And our task is to process Q queries of the form, what is the digit at position k in the string? So the first line of the input will be Q, the number of queries, and Q can be as large as 1000. Then follow Q lines, each containing one integer that can be as large as 10 to the 18th. Notice here if k was small, if it was only up to 1,000,000, we could just generate that string and answer the queries in O of 1. But here Q is very large, so we need to find an algorithm that works in O of 1 or in O of log n to answer these queries fast enough. So let's go to the drawing board and try to come up with an answer. So we were asked to find the digit at position 7 and 19 and 12. So let's write down what we need to do. So we will be given an index and we need to find the digit at that index. Okay. So before we do this, let's notice something. Like this 4 here, the answer for the second query, this 4 belongs to this number, it belongs to 14. So we could ask ourselves, if we are given an index, can we find the number that this digit belongs to? So what is the number that contains our digit? And before answering that question, let's ask an even simpler question. Like we are interested in this number. Let's just know for now what is the number of digits in our number. If only I could write. So how could we know, given an index, what would be the number of digits in our number? And this is not too hard to find out because our string comes in blocks. We have this first block that contains 1-digit numbers, then follow this second block that contains 2-digit numbers, and so on. So our first block goes from index 1 to index 9. Then the second block starts from index 10 to what position? This is not too hard to find out. So how many two-digit numbers are there? So they start from 10 and go all the way to 99. So how many are there? Let's apply the rule of thumb. So we need to count all numbers from 10 to 99. So this would be 99 minus 10 plus 1. So it's 100 minus 10, which is equal to 90. So there are 92 digit numbers, and since each one of them holds 2 positions, so this block will hold 180 positions. And since it starts from 9, then this will end at position 189. And the following block will start from position 190 and go up to what value? So how many 3-digit numbers are there? So they start from 100 and go all the way up to 999. So this is, we could do the same thing. So this is equal to 8000 minus 100. So this is 900, and since each one of them takes 3 positions, then they will take 2700 positions in total. So now if we are given an index, we could we could just see to which block it belongs. Now we have these limiting values, these boundaries that would tell us which block, how many digits are in our number we are looking for. Okay, so now let's say I am looking for the digit at position 107. Okay, so I can just check out here. It surely belongs to this second block because 107 is between 10 and 189. So I answered this question, no problem. So now let's try to answer this question. I don't know what my number is, but let's call my number x. So I don't know what x is, but I know that x is between 10 and 99. That's for sure. And this reeks of binary search again. So I know my number belongs to some interval, and I have a way of checking if I pick any number here. I know I have a way of checking or if my picked number is smaller than x or if it is larger than x. Then by using binary search I can just keep iterating until I get to x. But how can we do that? How can we actually know if our picked number is greater than x or smaller than x? So we know that our number contains this position. Since it is a two-digit number, then this position might be the first digit or the second digit, but in both cases I know that it belongs to this x. Okay, so let's try to do binary search here by hand. So this is my lower bound and this is my upper bound. So my first mid would be 50. These numbers are not exact. I'll just do them by hand to see what just to get an idea of how this would proceed. So let's check whether or not our number is 50. So at what position does 50 start? So we know that 10 starts at position 10 and 11 starts at position 12. But why? 11 starts at position 12 because 11 minus 10 is equal to 1, and the difference, and each number takes up two positions, so 11 will start at 10 plus this times 2, which is 12, and 15 will start at 15 minus 10 times 2, which is plus 10 because 10 started at 10. So this would start at position 20, and that's correct because 4 was at position 19. See, if I have a number here and I know that this 10 starts at position 10 and I know that each number holds two positions, then it's very easy to know at what position 50 starts. So we could just do 50 minus 10 times 2 plus 10. So this is 40 times 2, which is 80, plus 10, and this gives me 90. So I know that 50 starts at position 90, but I am interested in the number that contains 107. So 50 is not it. I need to go larger. So then I will bring my low to 50 now. So this is my low, and my high is still at 99. So I need to get a value in the middle here. Say I pick 75. So 75 minus 10 times 2 plus 10 gives me 65 times 2 is 130 plus 10, that's 140. But now it's larger than 107. So I need to bring my high down to 75, and now my mid will be somewhere in between, so say 62. So let's try 62 now. 62 minus 10 times 2 plus 10. This gives us 52 times 2, that's 110, plus 10, that's 120. Still larger than what I need, so I'll bring my high here. A value in between here would be 56. So 56 minus 10 times 2 plus 10 gives me 12 plus 10, no, 46 times 2 gives me 92 plus 10, that's 102. Still too small, so I'll go larger. So say 58 or 59, say 59 minus 10 times 2 plus 10, this gives me 49 times 2, which is 98 plus 10, which is 108. A tad too large because I need a value that is smaller than this. So 58 will do it. Minus 10 times 2 plus 10 will give me 106. And see here, at this time my low and high will be equal, and I will get that the value that contains 107 is actually 58. So using binary search, I could find my number. So we will find this using binary search, and in this case my number is 58. And I know that the position that it starts at is 106, and the next position for 59 is 108. So I know that the digit I'm interested in belongs to this number, so I can just take the difference. Here I could, for example, use some arithmetic and keep dividing by 10 or taking modulo 10 or something like that to get to the digit that is next to the first digit. Or I could, for example, convert this to a string using the function toString in C++, and this will give me a string 58, and this is position 0 of my string, and I am interested in position 107 minus 106, which is 1, so this will give me this 8, and then I will just print 8 as my answer. So that's pretty much it. To sum up, we will be given an index. We are interested in the digit at that index. So the first thing we will do is to find the number of digits in our number. And to do that, we just create these blocks, and we saw how to calculate these boundaries. And we'll find to which block our number belongs to know how many digits are in our number. And once we know the number of digits, then we will define these boundaries. We will know between which two numbers it belongs. So if it were, for example, a 3-digit number, we would know that it's gonna be between 100 and 999, and then we will use binary search to pinpoint what position our number, to pinpoint the starting position of, to pinpoint the number whose starting position includes our index. Something like that. So once we know that number, we know that our digit will belong to this number, so we will just take the difference between this index, and so it's gonna be index minus starting position of our number, and then this will give us our answer. So that's pretty much it. Now let's check out the code. So this is our code. We'll start by reading the number of queries, and since we're gonna need powers of 10, I'm just gonna calculate them or pre-calculate them. I don't want to use the pow function because it's not reliable. It might be reliable in this case because we're just calculating powers of 10, but as a rule of thumb, I'd rather not use it. So to calculate the powers of 10, I just initialized my array with ones. So power of 10 of 0 will be just 1, and then I will go from 1 to 18, calculating my power recursively like this. So power of 10 at I will be just power of 10 at I minus 1 times 10. Pretty straightforward. Then I will process my queries. So for each query I need to scan my index, and here pay attention, it needs to be a long because it can be as large as 10 to the 18th. Then I will declare a few variables. So this is to calculate the number of digits so far, and this is to calculate the number of digits before the actual block. As we saw here, like if I am at this block, I would like to know what is the number of digits before this block to know what is the starting position of this block. And I will also I will do this to find out the number of digits of the number that contains the digit at this index. That's a mouthful. So I'll go from 1 to 18, and I here represents the number of digits. So first, for the one digit number, the number of digits so far will be like power of 10 here. At 1 will be 10 minus power of I minus 1, which will be in this case 1, times 1. So the digit so far for the first block, as we saw, is 9. So if the number of digits so far is greater or equal than my index, like for example if my index was 7 and I got 9 so far, so I'll just stop because I know that 7 belongs to this first block. So if that's the case, I will just note that the number of digits in this case is I, and I'll just break. Otherwise, I'll continue and I'll just keep track of the number of digits before actual block. So if my number belongs to this second block here, then I will actually stop in the second iteration of this for loop, and digits before actual block will hold the value 9. So I will know that my actual block, the block of 2-digit numbers, starts at 9 plus 1. This will come in handy later. So this is just to find out the number of digits in the number we're looking for. Now that we know the number of digits, we can proceed to do binary search. So my smallest value will be the power of 10 of number of digits minus 1. So if the number of digits is say 2, so this will give me power of 10 of 2 minus 1, which is 10. And the largest value will be powers of 10 of 2, which is 100 minus 1, which is 99. So that takes care of that. And this best value is actually the value of the number I'm looking for. So I will initialize it with 0, and every time I get a number x whose starting position is less than my sought position, I will update my best with it only if it is greater than my best. So like in this case, I will first update my answer with 50, then this was not valid, this was not valid, this was valid, it was better than 50, it was less than 107, so I'll update my answer with 56, then 59 is not valid, and finally I will update my answer with 58, and that will be the final answer. Moving on. So once I find my best value, I wanna recall its starting position as well. So I'm declaring a variable for that. Now to the loop of binary search. So as usual, while low is less than or equal than high, then my actual value is just high plus low divided by 2. This is the actual value here stands for mid. Then my the starting position of this actual value will be equal to the digits before actual block plus 1. As we said here, if I am dealing with 2-digit numbers, the number of position before starting block would give me 9, plus 1 would give me 10. So this is to calculate the starting position of my block. Then for each value, like to calculate the starting position of the actual value, I'll just take my actual value minus the power of 10 of number digit minus 1. As I was doing here, like since I was dealing with 2-digit numbers, each time I was taking that value minus 10, which is actually 10 to the 2 minus 1. And I will multiply that by the number of digits as I did here times 2. So that's it. And if my starting position is less than or equal to index, as I did here, like in these cases when it was less than indexed, I made it larger. So I first checked if it is greater than my best value, then I will update my best value with actual value, and I will set the starting position of best value to starting position of actual value, and I will bring my low to mid plus 1. So smallest value would be equal to actual value plus 1. Else I will just bring down my high to mid minus 1. So largest value is equal to actual value minus 1. And at the end I will have found this best value. But as we saw, it's not guaranteed that this index will be like the starting position. All what I know is that it belongs to my number. So as we said, I will convert it to a string and I will just print the digit at that position. So I'll convert my number, so I'll create a string number which is gonna be equal to string of best value, and I will print the digit at position index minus starting position of best value. And that's pretty much it. So let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.